everyone, welcome to the channel Knowledge Star, Continuous Knowledge Excellence. My name is Nisha Masroor. In this video, we will get to know about how to make a polymer molecule compact. Now, our expert Professor Bohidar, who is associated with National Center Excellence in Agro Nanotechnology, Terry-Dika Nanotechnology Center, India. He has 31 years of academic experience in teaching and research. His area of expertise includes nanoscience and nanotechnology, nanobiointerface science, soft matter science, polymer physics and biophysics. So, to get complete information, watch full video without skip.
How do we make the two macromolecules or polymers or biopolymers come together? They are swimming far away from each other in the solvent. Principle is same. You create a dehydration process. Try to take out the hydration water from the surface of the biomolecules. And the simplest way of doing this is add a non-solvent which has got hydrogen bonding possibility with water. So the water molecules will slowly recede from the surface of the biomolecule. Try to form hydrogen bonds with this non-solvent, which in this particular case can be acetone, can be ethanol, or any simple primary alcohol will do that job very effectively. Soft chemicals only, no hard chemicals. Now that will bring the macromolecules together, or if it is a one molecule, the segments will come together. Once they are close to each other, then they will start interacting through electrostatic forces. They will bind each other to each other and form a charge neutralized complex, because the positive and negative charges will overlap. The overall charge on that will be very, very low. So that will form a complex, hydrated, and it will stay in the dispersion phase. And in reality, this will look something like this as shown in the cartoon here. So we have biomolecules floating. This drawing you have seen earlier, but I am telling the same thing in a different language now. You have biomolecules swimming here. I have added a primary alcohol to it. Alcohol will now drain the biomolecules of their hydration layer, because water will bind to alcohol with higher affinity. So the molecules will get dehydrated. They will start now looking like these, which are much more compact than earlier stage. It was extended, now it is looking more compact because hydration layer has been lost. Add more alcohol to it. Then this will form a compact structure like a sphere, which has a typically size of about 100 nanometers, 150 nanometers, and has turned into a nanomaterial. But many of these nanoparticles will cluster together and form large droplets, macroscopic droplets. Okay, and those droplets will undergo coalescence, and a cosorbate phase will now emerge from this dispersion, which is dense, as it is going to sit at the bottom of the reaction vessel. And those particles, collapsed particles of the polymer chain, which have not participated in the aggregation process, will continue to remain dispersed in the supernatant. So the homogeneous liquid you started with, it was a solution of biopolymers, has now turned into a two-phase liquid. One is the supernatant at the top, which is mostly this solvent with a small concentration of polymeric nanoparticles, and a dense phase at the bottom where the water content is low, polymer content is extremely, extremely high. And this concentration in the cosorbate phase can go to really very high level. It can be something like 100 grams per 150 grams per liter, which one cannot prepare at room temperature in a normal condition. So these are very, very special materials, very dense phases of the polymer or biopolymer. And it got a lot of applications, biomedical applications. So we'll not go into that. But our target is capturing these nanoparticles which are sitting in the supernatant. So this can because these two have a clear density difference, you can decant this, take away the nanoparticles which are swimming in the supernatant, a purification process through centrifugation, and then you have a clear dispersion of biopolymer nanoparticle. You want to turn them into a powder and collect it and store it in a bottle. Then you do dialysis, lyophilization, then you have a powder. Or if you don't have that facility, you can send it to very slow heating in an oven at 40 degree or so. Let it dry up over 48 hours or so. Don't keep the temperature high, that will create disturbance in the structure because they are all biomolecules. But if at 40 degrees Celsius, left over 48 hours, it will dry into a powder. But the best is to do a lyophilization experiment. So this is what I've been telling now. This is the dense phase, which is the coarser here. And this cloudy, this thing you see, the suspension mist here, these are all nanoparticles suspended in the supernatant. And this is what needs to be collected. And through water centrifugation and then lyophilization to get the powder out of it. And this I have described yesterday. The same thing I am saying today. We start with a situation where the biopolymer is dissolved in water. That biopolymer is not soluble in ethanol, but ethanol has miscibility properties with water. So ethanol will mix with water very nicely through formation of hydrogen bonds. At a particular concentration of ethanol, about 45% or 46%, you will see the turbidity going to the maximum. This is turbidity measured at a wavelength of something like 450 nanometer. Okay, and this cartoon tells you how the phase separation is taking place. Most of the aggregates are staying here, which is here, and few nanoparticles are suspended in the supernatant, which is corresponds to this. Driving the non-solvent concentration or the organic phase beyond this will ruin the entire experiment, and your experiment is dead, which means the turbidity is now here. So you have lost all the material to sedimentation. That is a failed experiment. Therefore, I repeat, the control has to be very systematic. You do a titration in a very systematic manner to drive the homogeneous one phase solution to a two-phase liquid-liquid phase separation. This is a liquid-liquid phase separation. Here, one liquid, one, this is liquid two. Low concentration of biopolymers, high concentration of biopolymers, high density. So you have two materials now ready with you. Now, this strategy has been utilized very extensively for the preparation of nanoparticles.
I hope you liked the video. If you want to see these type of videos, please do comment. We will definitely look after them. Thank you.
For more updates, subscribe to our channel, click the links shown on the screen to stay connected.